Hello. 1, 2, 3. Yes. Okay, so I think it's time to start. So good afternoon and welcome to the talk. In this talk I will talk about, PyPy. We will see later what it is and how it can help you to have more performance in your program and make it run faster. Some notes about me. I am Antonio Cuni. I have been a PyPy core developer since 2006. First doing my master thesis and the PhD, and then as a normal open source contributor. I'm also known for other projects in the open source world like PDB++, VMProf, CapMPy, also a bit of CFFI, and etc. Here are my Twitter handle and some links if you want to know and find something more about me. So first, let's start with an easy question. Raise your hand if you use Python. Ew, surprise. Ooh. So, raise your hand if you have ever had a performance problem with Python, like it's too slow. So, yes, most of you. Some of you didn't have, so lucky you, but yes. So why do you use Python if you have performance problem? Really, I mean, Python is not the right language for having performance code because it's slow for many reasons. Like it's intrinsically slow somehow because it's an interpreted language. It has a virtual machine which is good but is not the best in the world, and etc. Usually when I ask this question, people answer me a couple of things, but in particular they tell me that Python is simple, it's very easy to program with. It has a lot of libraries. It has a very strong ecosystem, so everything just works, and you can find any library for the task you need, and etc. And yes, most of the time these are the question why you use Python. But actually, why does all of this happen? Have you ever wondered why NumPy has been developed in Python and not in PHP? Why this strong ecosystem is in the Python community, but other languages and other communities don't have this nice ecosystem and everything. I thought a bit about it, and I think that the real strong point of Pythons are more low level, and is the fact that Python as a language lets you to have a very expressive and simple APIs from the point of view of libraries. So if you have a library developer, you can write something which your user, like the normal programmers, can use in a very simple way, in a very nice way, in a way which connects all the points together very easily. And that's why then all the ecosystem develops. And and in particular, Python has a uniform time system, like everything is an object, so everything fits together very well. And it has the ability of building powerful abstractions on top of the low-level details, so that you, as a library user, see just an easy way of doing things with all the details hidden. So let's do a very quick example of what I mean by this. At some point, I Googled JSON array example Java. And I found this kind of code in which, well, to do something in Java, to read some data from a JSON array, from a JSON file, you do something like this. And, well, it is kind of code. I don't want even to comment it. It's just, it looks like this. If you do it in Python, it looks like this. And I think that all of us agree that Python is much better, nicer, and simple, but they do the very same thing. But the powerful of the Python type system and some of design choices give you this ability of writing the JSON library instead of the Java version. So far, so good. We like Python. We have a nice ecosystem, powerful APIs. However, if you think about it, whenever you do a program, at some point at the core, there is what you really want to compute, what you really want to do, what you want to print, what is your output. And then you have layers and layers and layers of abstractions, which are libraries which make use of other libraries, which then gives you an easier way to access things and etc. And in a language like Python, unfortunately, all these abstractions have a cost. So here, I just, in the layers of this diagram, I just put some of them, but you can have different ones. Like, for example, every time you put something inside a function, it's better as a way of writing your program, because you split your functionalities into function and method and classes. But every time you call a function in Python, you have a cost. And if you use the iterator protocol, which is very nice, is what it lets you to write for something in something else, this also has a cost. And also Python, because of the way it works, in the inner way it works, it creates a lot of temporary objects. Every time you call a function, it creates a temporary object for the frame. Every time you call an iterator, it creates a temporary object for the iterator object, and etc. In particular, yes, temporary objects are killing performance in Python. You find them everywhere, even when you don't know. For example, if you have bound method, like here, I have a class with a method which returns 42. It does nothing, and I can call it in two different ways. One is the classical way. This one, everybody does this to call a method. And but what happens is that Python creates a temporary object, which is a.foo, and then calls it. And the temporary object is a bound method. What I can also create it explicitly here, before, and then call it later. And if I run this code on CPython, I think it's running now. Yes. We see that calling the method normally takes this amount of time, 113 nanoseconds. And if I call the bound method, it costs less. And now you could go out and say, OK, now we know how to optimize our code. But it's very wrong, because, I mean, what happens is that your code, it's worse, because you have these bound methods everywhere, and then you have this optimization that makes your code cluttered. So ideally, when you write a program, you would like to think about concepts, not implementation detail. I want to call a method. I don't want to think that CPython creates a bound method, so I want to avoid it, to do it in a loop, and etc. However, in the real world, these implementation details leak to the user. So if you want to write performant code, you have to think about them. So in Python, the Python world, if you really want to arrive at writing the fastest possible code, you have this tension between the abstractions, like I want to write my nice code, nice libraries, and etc., and performance. I don't want to put this code into a function because it costs me. And you can see that there is a trade-off. So when you talk about Python, normally most of you use CPython, which is the normal standard interpreter which everybody gets from either the distribution or from the internet. What is the classical way of approaching the problem of performance using Python? Well, the first is to work around and do something in your code, like the example of bound methods I did earlier. So you can make your code slightly worse because maybe in this for loop you do this slight optimization and then you do something else and etc. So you can win some percentage of speed by doing this. The second is to work around the issue by changing the language specification. Like, for example, at some point in Python 2, we had the range, which returns a list, but sometimes you just want to iterate over the values of the list without creating the temporary object of the list itself. So they invented xrange, which does the same without creating an actual list. Or if you want to iterate over the keys of a dictionary, well, you don't want to create the temporary list holding the keys, so you can iterate on the iter keys. Or ints and longs have different properties, so sometimes longs are slower than ints and etc. Or if you have a list with numbers, in Python, it occupies a lot of memory, and if you want to store it in a more compact way, you can use array.array in the language, or a NumPy array, for example. However, all these things are easier to implement from the language implementer point of view. If you are a CPython developer, it's easier to just add xrange. But they are harder to use from the user point of view. And they clutter the language unnecessarily, because then you as a Python developer needs to remember range versus xrange, or iterators or list and etc. And I think in general it's not really Pythonic. Note that all of these examples have been solved in a way or the other in Python 3, but this was just to give the rough idea of what I mean by changing the language specs to work around the performance problem. The third classical approach is try to stay in C as much as possible. Like, instead of running Python code to multiply all the numbers in a list, I use NumPy, which is a library which is written in C, so it's much faster because... Is it running? Yes. Because, yeah, it took more just because it ran much more loops than the rest. But the result per loop, as you see, it's much faster than Python. Because it's written in C. So C is faster than Python, so yes, we are all happy. And the fourth possible thing you can do if all the rest didn't work is to rewrite part of your code in C, or something which at the end it's implemented in C. So you can either write a C module which includes python.h and write it by hand. You can use a Cython, which is a nice tool to emit this kind of code automatically. You can use CFFI, which is yet another library to wrap Python code. So basically, this rewriting C approach is also known like as the 90-10 rule, in the sense that you assume that your code contains a huge block of a small piece of code which represents a huge percentage of time spent. So to run this code, I spend this time with all the abstractions. So you rewrite in C, so that by rewriting a small amount of code, all the rest, the total amount of time of your program becomes much less. So, for example, by rewriting in C this score of computation here, you go from this situation to this, and you see that, yes, your program is becoming faster. The yellow box means that it was rewritten from Python to C. But, yes, I still have to pay a lot of abstraction cost for all the layers that I had to write on top of this C core. So, what I can do? Well, I can rewrite also the other layers in C. So I arrive at this situation, and you see that now, comparing to the original situation, the total time spent in my code is much less. So yes, success. However, I still have the abstraction cost, because even if they are in C, I still pay a bit of penalty for calling functions, creating classes, and etc. And then we have this really, again, this tension, because to get the result, I had to rewrite parts in Python, which is a worse language than Python, or I have some code written in C, which is even worse, and etc. So my code quality overall had a regression. Moreover, now that your big box is smaller, in percentage, the Python parts are relevant again. So what you can do? Well, you can do the same for each blue box and again and again. So at the end, you arrive at the point in which everything is written in C and your nice Python program no longer exists. So if you are in the high-performance computing world, sometimes you end up seeing Python as a glue-only language. It's just a language which you use to stick together all the parts which are very performant and written in a more efficient language. And as I said, you always have this trade-off between speed and code quality. So the idea of PyPy, or one of the ideas of PyPy is to solve this issue. And I will show it now how. So what is PyPy? It's an alternative Python implementation, like Python. Ideally, you should not see any difference. Like, I can go here, type PyPy, and what I get is a Python prompt, and I can do, it's very boring because I can do the very same things that you do in Python. Yes, it works. So no difference to the user. However, internally, it has a JIT compiler, just-in-time compiler, which takes parts of the Python code and emits fast assembler code for it. So the end result is that it is much faster. How much faster? Well, it's a wrong question. Because it really depends on your code. So I cannot tell you PyPy is 2 times faster or PyPy is 10 times faster. It would be easy to just say it, but it's not true. Depending on the code, I have seen real-world code in which PyPy goes 80 times faster, sometimes 10 times faster. A good guess is that on random code that you don't know anything about, maybe it's 2 times faster, but then you can optimize it more specifically for PyPy to be to have more and more speed. Sometimes it might happen that the PyPy program is just a bit slower than CPython. Well, you have to try. But usually, if you optimize for PyPy, you can really reach very high speedups. It's not perfect. It's far from being perfect. Like, I'd say that ideally I would like to think about concepts and not implementation details about performance. Well, PyPy fixes a lot of the CPython problems in terms of performance, so you don't have to worry about them. You don't have to worry about function calls, cost, about classes, and about anything. There are other implementation details that leaks to the user, like the JIT has a warm-up time, so you have to take it into account. The GC works in a different way than CPython, so you have to think about this and etc. So I'm not saying that PyPy solves everything. However, it has a lot of qualities, and in particular is that it is written in a way that your Pythonic code, your idiomatic code is fast. It's really written with this use case in mind. You don't have to write non-idiomatic code to make it fast. Just write normal code as you are used to, and PyPy will make it as fast as possible. And in particular, abstractions are almost free. Like, as I said, I can put all the code in functions and classes and etc. And the PyPy JIT is smart enough to remove all the overhead. And compared to CPython, the better the code, the bigger is the speedup. Because if you start from the same code base and then we add abstractions on top of it, every abstraction costs nothing on PyPy and costs a bit on CPython. So the better the code, the bigger the speedup. So, for example, this was our original situation again. What happens with PyPy is something like this, in which the JIT compiler optimizes everything, so we have a total cost which is much less, and a total speed which is much faster. But I don't know if it's big enough, but also you see that the abstraction cost here is really shrinked. I mean, there is still a bit of cost of abstraction, but most of the layers are just removed. So what's left is just the core of the computation, what I really have to do. I cannot remove it. And the idea is that since you have these nice qualities, Python is again a first-class language. It's no longer just a glue. You can write your code in Python, your business logic in Python, and you can use all the Python nicety and nice features to have a nice program with parts which connects together using classes and modules and iterators and all the things that makes Python a good language. I have an example, but I don't have time to show it because it's only 30 minutes. If you are interested in the details of this example, you can click on this link, and it's a talk that I gave at EuroPython last year. And it's an example in which basically I have an image processing code, and I show the first version of it, which is just the computation. Like everything is in line, all the computation are in the main loop, and etc. And I see that on PyPy it's faster than CPython. Yes, good. But then I start to make it better. So some of the code is put in a function, then the function is wrapped into classes, and then I use the iterators to iterate over all the points in the image. So at the end, I have a very nice code, which is testable and readable and whatever, maintainable. And as you can see on CPython, every iteration of refactoring brings some slowdown. And you have to know that the y-axis is very different here. It's not the same y-axis. So on CPython, the first version was 5 frames per second, and on PyPy it was almost 300 at the beginning. And the more you go, you see that on PyPy, apart this, which I'm not going into details to explain what happened here, basically you don't pay any cost. At the end, you have your nice program, which is still very, very fast. And on CPython, the performance drops. So it went from starting like at 60 per faster to the final result, which is 400 and something times faster. I mean, it's impressive. And really, if you look at the code, it's very nice, basically. However, we still have a big problem, because so far, so good. Yes, you can go and try and install PyPy, and you think to have solved everything. But there is still something which prevents a mass adoption of PyPy, especially for you like data scientists. It's a C extension, because you have a lot of libraries which are written in C using the CPython C API, like python.h. And on CPython, you have this kind of situation in which the library is written in C, the yellow box. The CPython API is the purple box, and it's very thin because, well, it's written for it. PyPy has to emulate all the CPython internals because we have a completely different internal data structures. And at the time of speaking, this emulation layer works, but it's very, very slow. So we have this kind of situation. So what you win because the Python parts are faster, you lose because calling the C is slower. But we are working on it. We are trying to make it faster, and we will make it faster eventually. The current status is that, yes, we have this compatibility layer, which is called the CPyExt. Most C extensions just work. You can pip install NumPy, SciPy, Pandas, and all the other nice stuff you use. However, as I said, it's a bit slow. So depending on your use case, your program might not be faster on PyPy than CPython. In general, if you want to call C and be fast on PyPy, you should use CFFI. CFFI is a very nice library for calling C, and even it works both from CPython and PyPy, and it's super fast on PyPy, so it's the good choice if you want to try it. As I said, we are working on the speed of the compatibility layer. So this was the situation 1 year ago, more or less. I have some micro benchmarks on calling C. You see, they are normalized to CPython. So the blue bar is a CPython, and on all benchmarks, PyPy 5.8 was very, very slow, up to 10 times slower here. And if I show you also the results of PyPy 6, it doesn't work. Yes. Surprise. Yep. I don't know why it's okay. Good, better. So the red bars are the result on PyPy 6, and you see that we are faster on almost everything, much faster than before, and sometimes we are just faster than CPython at calling C. I mean, we are faster than CPython that at doing the CPython stuff. We are emulating it faster than it can do it natively, basically. So, but as you see, we still have problems like here, this micro-benchmark, which allocates stuff in C. It's much worse on PyPy, so it really depends. You should try on your code base and see what happens, basically. So the future status, hopefully, is that all the C extension will just work as now, and the parts of your code that are written in C will be as fast as today. Like I cannot optimize the C code because I don't have any impact on it. But your Python code will be super fast, so it's the best of both worlds, and the PyPy will be the default choice for high-performance computing if you want to use Python. Personal estimate, I think that with 6 months of work on optimizing this CPyX layer, we can arrive at this point. It's just a random number, I don't know, because you never know what problem you will encounter, but it's my personal estimate. As usual with open source, the problem is finding money to do it, so if your employee or something is interested in this, please talk to me and yes, give me a big check and I will go to away. Yes. But yes, that's the plan basically. So I think that's all, and we have some time for question, I think.
In practice, at least almost every day, the people who work with scientific Python, like myself, use a mix of C with, I don't know, scikit-learn, NumPy, and so there are the extensions, and there is, I don't know, Numba. There is a lot of framework, Cython, that helps, and now we have an eye on all of them. So how would you put in such scenario, which is quite usual, I guess, with this audience, PyPy? So how should we modify our usual workflow in order to use it?
That's a good question. Basically, the answer is I don't know, because it really depends on your code base. But I have seen example in which you really have two big parts in the code. One which is like numeric stuff, which uses SciPy or NumPy heavily, and the other is a pure Python thing that maybe receives frames from the internet and do something with JSON and etc. So depending on the case, maybe PyPy is worth because it really makes the Python part very, very fast. Maybe sometimes it's not the case, really. The thing is to try. In general, you should try to avoid crossing the border too much at the moment, because as I showed in this, where is it? Wow. Why it's not working? Yeah. Yes. In this, basically, this diagram means that every time you go from the blue box to the yellow box, you have to pay the penalty. So if you write your code to call a lot into C, then you pay the penalty a lot. If you manage to rewrite it in a way that you prepare your data and then you pass it to a nice C function which does the work, then you cross the border only once, and then maybe it's faster. But it's possible that if you really use a lot of numeric libraries, at the moment PyPy is not the best tool to use. But this was like also my way of thinking in the future, and maybe the future is not so far as I said in the last slide. Does it answer the question?
Yeah, and just to complete the question. So this is from the user perspective, like I'm a user, but from the point of view of software developer perspective, like open source projects like the one that I mentioned, I don't know, scikit-learn should use PyPy in some way, should more than, I don't know, Cython, Numba.
What libraries can do is to write their code to be easier for PyPy to optimize. So some libraries are trying to be compatible with PyPy, like they run the test on PyPy, so we can ensure that they work. But also, there are ways in which you can write your code so that the PyPyJIT makes a better job. Like, for example, something that I did in one library I developed, it's CapMPy. It's a library for reading and writing CapMProto streams, just a serialization format. And it was supposed to be super fast, both on CPython and PyPy. So for CPython, I had to write Cython, because, well, it was the right thing to do. And on PyPy, I undo the Cython. Like, I just use a pure Python module, and on CPython, I compile it with Cython, putting annotation in an external file, and on PyPy, I just use the pure Python version. So in PyPy, usually the pure Python version is faster than the Cython version. So you can do this kind of things, like using Cython only on CPython and not on PyPy. Also, a lot of other libraries have what they are called the speedups, the C speedups. So you have the pure Python implementation and also a module which is compiled in C and gives you a faster version of the same functionalities. Like the simple JSON package had this kind of packaging. But in PyPy, the speedup is a slowdown. So if you use the pure Python version, it's faster than using the C version. So the library, the library authors can package the system in a way that it uses the C version only on CPython, but not on PyPy. But yes.
Thank you.
Quick question, will it work together with number? Because number offers like automatic parallelization and also offers like a CPU target, a lot of other nice things. Would it be useful, or would it be possible to use PyPy in combination with number?
Good question. In principle, probably yes. In practice, I think that number is really tied to the CPython internals. Right now, I don't know how it works exactly, but in principle, number is something that gives you a callable which does executable code, so in theory, yes. Note that, yes, number is also a JIT compiler for Python, but it's completely different way of doing things. It's a method-based JIT, so it just compiles the code in your function, and it cannot really remove the abstraction overhead I was talking about, because if you give it like a complex system in which you have classes and objects and etc., number is probably not very good. But if you just have a while loop, then yes, probably number can work.
We are kind of running out of time. I'm
yes,
sure you can reach Antonio.
Yes, feel free to stop me and ask questions now.
Sorry.
Okay, so we can start. So, good afternoon, everybody. My name is Ahmed Ratnani. I'm working at the Max Planck Institute for Plasma Physics, and I'm going to present a kind of compiler for Python that uses Fortran as a backend language. So it's not similar to PyPy, because what we want here is really to get a Fortran code that you can use in your application, or you can link to low-level code or call it also there. So the reason why I started this work is that in our institute, we are working in a numerical mathematics division with physicists. And so our aim is to write complicated algorithms that are parallel and then provide physicists with a low-level code that they can use. So basically what we would like to have, like all of you, to have the ability to write fast code faster, and to allow for people from different fields like applied mathematicians, computer scientists, or physicists to collaborate easily. And so we would like to have codes that are parallel and portable, that work on different architectures. And we would like to simplify somehow the path from a prototype to a production code. So if you think about all these motivations, then you will think about Python for sure. But you saw in the last talk that Python itself is not really good for intensive computations. So the other point of view that you can have from these motivations is the notion of domain-specific language. So domain-specific languages are really well suited for this kind of problems, where you increase the productivity. Okay. So there are different solutions to accelerate your Python code. This you already now you know it. You know NumPy, you know Cython. There's also Hope that is just-in-time compiler like NumPy, but NumPy works also on GPUs. There is also this Fortran compiler, let's say, that converts Python code to a C++ static code. And it has also, in addition, explicit parallelism using OpenMP. So this is somehow the approach that we are using. And so one of the nice things that I like about NumPy, for example, is that it relies heavily on the use of decorators. And this is something that we try to use also. So I will first present some benchmarks, so just to see where we are. So here there are 4 examples where I use Python, Cython, NumPy, Fortran, and then Pyccel with either a Fortran compiler or Intel Fortran compiler. So you can see for the first example that Intel is really doing a very, very good job. And also for the second and the third one. And this is mainly because Intel compiler knows really how to optimize code. So basically what we do with Pyccel, we are not doing any optimization. We are just translating the Python code to Fortran. But we know that Fortran compilers are very, very good. So they produce very optimized code. And even with the GCC example, you see that we are twice faster than Fortran that was already optimized. So you can see other speed up that we have, and in general, we beat all of them, and this is really thanks to the power of Fortran. Okay, so let me explain a little bit how it works. So Pyccel is in fact just an extension of SymPy. What it does is that it converts your Python code to a symbolic expression. And then starting from this, you can add many things on the top of it. So you can add types on it. You can infer the type, for example. But you can also extend Python through commands. And this is what we did. So the first thing when you give a Python code, we run the syntactic verification on it. And then we use Red Baron for this. And what is nice with Red Baron is that it gives you the FST. So it's the full syntax tree. You have access to the commands. And it's there where you pass everything you want. So basically, this Pyccel gives you a language that is an extension of Python, but it works only on the command. So your code will always work. And this is nice because we ensure backward compatibility, unlike Cython, for example. And then once you do the syntax verification, there are either syntax error or maybe some limitation of Pyccel, because, for example, there is no try except in Fortran, and we don't handle this. So then we convert now this all these nodes or this AST to symbolic objects. So then we start really working in SymPy. And then whenever we see a command like a pragma, we can check if it is because we are using an accelerator. So for example, ACC for OpenACC or OMP for OpenMP. But we can also have types. So we can pass types of the function or class, for example, through the commands also. And we added also the notion of macro DSL, which allow us to map sentences of our internal DSL. You'll see this with SciPy linearlog.blaz, for example. And so once we do this, then we have a nice AST, and then we go through the annotation, and it's there where we compute the types of all the functions and so on, and we generate the code. And for the code generation, it's not really difficult. It's just again an extension of SymPy. Okay, so we handle different native data structures like numbers. We have also multiple precision lists and the arrays. And there are really two things that you need to that you need to keep in mind is that you can use Pyccel for imperative programming or in functional programming, which means that for the imperative one, we will be doing a source-to-source approach, just converting the sentences from Python to Fortran. But in the functional one, we will start manipulating the code. Okay, so we handle OpenAMP 4.5. Task-based parallelism is not yet available. We have also OpenACC, MPI, BLAS, LAPACK, and all of this can be done only through our DSL function. So just to show you how it works, it's very easy. You have your Python function, and you add this comment on the top of it. And this says that your function will take an integer, but the type of y will be inferred automatically. Okay, so you can do it with you can have interface of functions, which means that the function can have different types. So here we are not in just in-time compilation. The type is supposed to be known before. And then we can really play with it as we want. So we have static arrays also. And for example, this is an example on how BLAS is handled in this situation. So you can write a file called, for example, .pyh. So this is a header extension. And there you can just add the signature of all your function. With this, you can, with Pyccel, do from BLAS import srog, and you can call it really in the low level phase. So then you can end up with a code like this. So it's a kind of Python, but you see that the call here, if you know BLAS, you see that this is really the call in Fortran. So this kind of code will not work in Python. In order to make it work in Python, what we do is we use the notion of macros, and then we map the sentences between BLAS and the SciPy sentences. Okay. So the same thing can be done for MPI. You can call MPI in the internal DSL, or have it through macros using MPI for Py. So this code can be really converted to Fortran and works in Fortran. So here an example with OpenMP. So this is a matrix multiplication, nothing special. So this code will run in Python, but not in parallel. But if you use Pyccel, then you can have here, for example, a speedup where with one processor we have maybe 20 minutes, and using 28 processors we are less than we're a couple of seconds. Okay, so with OpenACC, the same thing. If you recognize how it works. So then we have another way of using Pyccel, which is embedded one. You can declare your function, which is a Python function, and then call a Pyccel function from Pyccel. And this will convert your Python function to a Fortran function. Yeah. Okay, thanks. This will convert the Python function to the Fortran function, and then returns it back as a wrapper using ftpy. And then now you can really work with it, and it's quite fast. Okay, so we added also code analysis, which means that you can take your Python code and check what is the arithmetic complexity or the memory complexity. And I hope that this kind of tools will help people writing better code, because then you will know how much exactly you are using your cache, for example. So we are building different kind of solvers now based on this approach, like a Chronicle solver where we have MPI that is calling BLAST, that is calling LAPAC, and so on. And all this code is being converted directly to Fortran. So just to summarize, Pyccel is really a very new tool. It's really, really new. It's a static compiler for Python using Fortran as a backend language. It competes well with the existing tools, and it allows you, in addition to this, to use some of third libraries that exist. And this is somehow what really makes it different with respect to other codes. So we'd like to add task-based parallelism. That would be nice, and also have some cache optimization patterns for programming. So yeah, the documentation is not yet up to date, but if you have any questions, just write me an email or contact me. Thanks. Any question?
We can probably take one question, if anybody.
Yes.
Maybe just show backup slide.
Sorry, yeah, backup slide, yeah. So there is, so this is not, this is just, let's say, a way of how I see programming with Pyccel. So basically you can, because with Pyccel you have a kind of meta-programming, and you can either implement really abstract nodes as an extension of SymPy, or you can really write Python codes that is completely compiled into Fortran. So the idea is really just not to convert only one function, but convert something that is complicated, maybe a module where you have functions that are calling functions, and this can use maybe classes and so on. So this is really somehow the idea of Pyccel. And yeah, so this is more for code analysis. So if you have a code like this, it will tell you how much of what is the arithmetic complexity that you are using. And if you rewrite it like this, so this is the matrix multiplication. If you have a block, you subdivide your loops into blocks, and then you are looking for the right size of the block to use to take benefit from the cache optimization. So with this, you can see also that now the computational intensity depends on the size of the block that you take. This is how it is done.
And I have a question. Like,
Yeah.
Together with the try except, which are the other limitation that you cannot use?
So normally, if you write an HPC code, you will not write a try except. So you really try to stick to something very basic. So there are try except cannot be handled this way. But we can still give it a meaning. We can still raise an error. But this will not be good for HPC application. Normally, the code should be really without any try except.
Yeah, sure. But other constructors that cannot be used?
I don't remember a lot. I think the main one is really the try except. Well, I should take a look at the code.
Thank you.
You're welcome. Thanks.
Well, afternoon, everyone. My name is John Masik. I come with the team of INRIA in Paris-Saclay, and I'll be presenting the new things in the last version of M&E Python. It will have like some nice pictures and some snippets that we'll be able to discuss, and hope to see you there.
Hi, my name is Sebastian. I'm from TU Ilmenau, and I'm presenting something very related to the talks we saw just now. It's about high-performance computing on GPUs. We try to do non-destructive testing, which is kind of important if you're sick and the doctor wants to know what's up with your body without destroying it. So yeah, if you were interested in that, come and visit me at my poster.
Hi, my name is Maria Terenchuk, and I am a postdoc researcher in computational neuroscience. So one big problem we have in science is reproducibility. And that's not just a problem in experimental sciences, but also in computational sciences. And even if the code is published with the scientific publication, often it's very difficult and time-consuming to prepare all the environment to make it runnable for anyone. So if you like to discuss more about reproducibility with me, and then welcome to my poster.
Hi, I'm Giuseppe from ATC Sustainable Solutions, and our poster shows all the whole data flow we implemented from the in-field data to our servers, and also to put it on the dashboard. So we developed many Python scripts to FTP automatic download and upload the data, and also to reshape and pre-process data, and also to implement KPI, key performance indicators, and decision tree to help our customers. There are managers of wastewater treatment plants to take a correct decision. So me and my colleague Marco will be available for any question at the poster. Thank you.
Yes, hello. I'm Neil Davis from the Department of Wind Energy at the Technical University of Denmark. And my poster is about the inverse process of what we just saw in the presentation here. So the presentation here was about taking Python and converting it to Fortran. I have a legacy Fortran model, and it's about how to expose it into Python. And so the poster talks about some of the challenges of working with legacy code. This was a program that was developed largely 29 years ago, and so how exactly you understand what's happening inside of it, and how you can make it work well in a Python ecosystem. So, thanks.
Hi, I'm Robert. We solve a highly nonlinear program related to electronic structure calculations, and on our poster we compare some algorithms accelerating convergence of such a problem. So it's a nonlinear problem solution, and so if you are interested in this case of problems, come and talk. Thanks.
Hi everyone, my name is Sylvain Gubian. I work in Philip Morris International R&D facilities in bioinformatics department. And I'm going to present a poster about, first one question, how many of you use R, statistical language? Okay, few people, so you may be interested in the poster because you probably know that, don't know if it works well, okay, that sometimes it's a bit of a mess dealing with packages in R. So we have developed a tool in Python to manage this properly. So this is mainly about that. Thank you.
Hi, I'm Christoph, also from TU Ilmenau. I brought a poster with me describing some of the problems that you have when trying to model analog circuits in Python or generally in open source. Most of it is proprietary company owned, so I don't want to do that, so I want to do it open source and found a way of modeling analog circuits and stuff using Python, and I'm happy to show it to you and to talk about your problems if you have something similar, and I'm looking forward to chit chat. Thanks.
Hey, I'm Thomas. Before I explain you my problem, if somebody of you knows, do you hear me? Okay, if somebody of you knows about software licenses or testing, please talk to me because I need to get to know something about that. But to the problem, I work with the Boltzmann equations, so kind of partial differential equations. And one problem which I'm currently having is, if you know partial differential equations, you need a position space. And if you have a boundary here, so usually if you want to do something there, and let's say you want to have something in first order, something flows from here to there, you get this new value from this one and the one in the other direction. So this is easy for a first order scheme. If you want to have a second order scheme, you need 2 points in that direction. So what happens if you have like 1 point to your left, it's a border, then you only have 1 point there in existence. So you have a problem. So if you have a solution for that, and I know there are supposed to be ones, I just can't find them, talk to me. Thank you.
Okay, so hello everybody. I'm an intern. My name is Alexis. I'm an intern at Saint-Gobain Recherche near Paris. And in my poster, I will mainly present a numerical tool for optical modeling of the properties of nanoparticles and how it can be used to monitor industrial processes, and also to better understand the optical properties of nano objects. Thank you.
Okay. So thank you very much. Just a very quick reminder. Tomorrow morning, after the first keynote, we're going to have the raffle for the 5 coupon discount, no, 3 ebooks you can get. Okay. The rule is if you are not in the room, you basically lose it. Okay. If you're one of the winner and you're not in room, you won't get it. Okay. Thank you very much.